Monday and Tuesdays, if you have to look at that over the weekend. It's the same type of thing where there's some code provided and some data. So it's mostly describing the output rather than reproducing the code. And as we go on through the semester, you'll be doing more of your own description and coding, but it'll be gradual, kind of step by step. So today we want to talk about approximating sampling distributions, and in particular the central limit theorem. So the context of where this is we have some population, and from this population we're taking a sample, and we're getting some data, the x1, x2, up to xn, and we are reporting some statistic. The book calls it T. Could be a test statistic, like in hypothesis testing, but it could just be a descriptive statistic as well, just to describe what the population might look like. So it's some numerical function of the data, and we want to think about what distribution, what's the probability distribution of T what's the probability distribution of T when we're sampling from this population. And many things we often leave fixed, like the sample size n, the sampling mechanism, is it a volunteer, is it a random sample, or something like that. If we're sampling in different groups, we usually leave that facet of things the same. But so what's the probability distribution? Right? And so by this we mean what are the likely values? And maybe not the specific value, but likely ranges of values if it's more continuous. Right? Likely values of T, and how likely are they? How relatively likely? So maybe the values of T that we would see just by random sampling, it wouldn't necessarily be a smooth curve or anything like that. It wouldn't necessarily be symmetric, but there's some kind of central value in here and some spread and some other patterns that might show up depending on things. And we want to know about that, right? And so one way of looking at that probability distribution, sometimes we can do exact calculations. We won't do that a whole lot. But under assumptions that you're sampling from certain probability models, then you have a certain sample size, then you can do probability theory to get some exact results, kind of as an approximation to reality. Right. Simulation we will do. So we've used this with our permutations to test hypotheses. Also use a simulation technique called Bootstrap that we'll really talk about on Monday. Right. And so this Bootstrap is talked about more in Chapter 5. So these chapters are not overly long. Some chapters we will spend more time on and augment more, but the sampling distribution 1 on 4 we don't spend a huge amount of time on. So we do move on to looking at bootstraps. Then the other way you can learn about these distributions is sometimes an approximation works. Right? And the main one that we'll use is central limit theorem. Right? So in the central limit theorem, some statistics, particularly the sample average, or maybe functions of averages, right, end up with a sampling distribution, a probability distribution. Right? So a graph that like this or whatever it ends up being pretty close to kind of symmetric and bell-shaped. And it would be centered here at the population mean. But under certain conditions, when we can approximate it well, we have a normal curve, we can talk about probabilities of being in certain areas, inside or outside, and do analytic calculations with that. And it's not exactly the sampling distribution because we don't know that the data are exactly normal themselves, but if it's close enough, then to 2 or 3 or 4 decimal places, it's reasonable accuracy. So If the chances are very small, right, it's still going to be very small even if we don't have it exactly matching the sampling distribution. So that's what's meant by this approximation. Right? Right. So that's the context. We want to know the sampling distribution of statistics. But any questions about what we mean by a statistic or why we're looking at the sampling distribution? Right. So, central limit theorem. It is a theorem proved in probability theory, and basically says something like this. So if you have some observations, x1, x2, up to xn, and each xi has a mean given by mu. That is, this is the population mean. So as you randomly sample one observation, it's sampled from some population that has that mean. Each xi has a standard deviation sigma. So that's like the population standard deviation. So population standard deviation, a little bit of abbreviation there. We're also going to assume that each xi is independent of the others, so that the measurement on one doesn't affect the other one. So they're not necessarily clustered with different characteristics by cluster. They're not necessarily paired. Not necessarily a time series element to it where it's kind of high for a while and then low for a while, but they're independent, right? Then x bar, the sample average, is approximately normally distributed. That is, the sampling distribution looks like the nice bell-shaped curve, and we write that it's approximately normal. It has mean mu, that's the average, and its standard deviation is sigma over the square root of n. So whatever each xi had, each individual value had sigma, the x bars have less variability because the highs and lows cancel out, and they go like that, right? And so this would mean that it's normally distributed with this mean and standard deviation. So we can draw an enhanced picture of what that sampling distribution should look like. So we would write, we could draw a picture of the sampling distribution, and we'd want it to be a little bit more nicer than that, right? Where there's a mu in the middle. Just kind of got a little bit out. There you come down a little bit more, so it's a little more bell-shaped. And then, the formula for the normal, that is plus or minus 1.96 standard deviations of a distribution contain 95%. So about that over to here to over here, you have about 95% of this total area, or 95% of the probability. That's an x bar here. I'll just erase that, make it nicer. This upper point would be mu plus 1.96 times the standard deviation for the x bar, which is sigma over square root n, or sometimes referred to as standard error. And then this one over here is mu minus 1.96 sigma over the square root of n. Right? And any particular interval you want to calculate probabilities for, you can convert it back to the standard normal distribution and look it up in tables, or use the computer to calculate probabilities under the normal density curve, right? And so that's just kind of the general statement about it. And so in practice, we typically say, or I think about that it's approximately normally distributed, and if I calculate probabilities for the chances of different events or tail areas or things, that it's going to be pretty accurate. The mathematical definition is a little bit more involved, right? So if you had those, if you had the x1, x2, up to xn, and you let z sub n Right, so x bar n is the average of n observations, right, going from 1 up to n. So you can think about a random variable x bar with that little index, means the sample size n. And you let Zn equals x bar n minus the mean over standard error, sigma over the square root of n. There's a concept called convergence in probability. Z sub n is then a random variable, and it's indexed by how many observations are put together. And the central limit theorem says that as the limit, as n goes to infinity, right, of the probability that Zn is less than or equal to some value, so this little z is a number here, right? The Z sub n is a random variable, so the probability that the Z sub n random variable is less than some point, right, that its probability distribution is less than or equal to z, as n goes to infinity, is the cumulative distribution for a normal. Right? So this nice symbol here is the integral, right, under the normal curve of this area, where this curve is the standard normal with mean 0 and variance 1. So there's a very mathematical definition saying that as you get a larger sample size, that under some basic conditions, like the mean and variance actually exist, that the distribution is not too heavy-tailed. There's a few, of course, in mathematics and so on, you can think of cases that are, what do I want to say they are? They're very bad cases. They're
Outliers?
They're outliers, but they're kind of the
Edge cases.
Yeah, crazy, funny cases. I'm looking for a word that I just draw, but the ones that are always the exception to the rule in mathematics. There are some distributions which don't have means and don't have variances because they're too spread out over the whole real line. But in practice, I'm not sure we ever observe those. Not too often, anyway. But anyway, as long as there's a mean and variance, and this makes sense to take the division, you're not dividing by 0 or infinity, right? Then the limit in probability ends up being this distribution. So you calculate that, right? So there's a mathematical definition, but we really will think about it in terms of, this, that we can act as if x bar is approximately normally distributed. And so then we can do calculations, right, to see how things go. Right, so let's look at a very practical thing of doing some probability calculations with this idea. Right? So let's look at a little example. So say somebody is a waiter at a ski resort, skis all day, work at the restaurant at night, right, and does that for a season. And this person works in Austria and makes most of the money on tips at the restaurant. Let's say that this waiter, based on experience, that the average during a particular shift, like an entire evening shift or something, earns about 150 euros. So kind of the euros, right, there, with a standard deviation of about 60 euros. So this is a mean, and this is a standard deviation. And so a new season, that's what it was, last season, and so they believe these values to be approximately true, right? And now, over the course of the season, this person is going to keep 32 records on 32 different nights, right? 32 different shifts spread out over a year or 9 months or something. So they're not exactly consecutive, they're pretty close, so independence might not be that true. You might have an event going on for a few days, and so it might be busier or something like that, but not too much, right? We can ask, what's the probability that the average Right, we're going to calculate x bar equals average of tips in 32 shifts. We can ask what's the chance that the x bar, this average, is going to be less than something like 130 euros. What's the chance that it's less than 130, given that the average is 150 and the standard deviation is 60? Well, we can't really do an exact calculation, right? What we need to answer this is we need the sampling distribution of x bar. Right? What is the sampling distribution of this average? But we don't know it, right? We have 32 data values. We don't know from this statement that the distribution is actually normal. Maybe it's not normal of the individual values. So we can't do an exact calculation or simulate it. And so eventually we're going to have this bootstrap where we have a different approach to simulating. But x bar is roughly normal for adequate sample sizes. This plot of 32 values might not be too extreme. We're not earning too small most of the time and then a few enormous values. It could be kind of, not symmetric, but not extremely, skewed or not massive outliers. It's not like $1,000 tip one night, I guess. So, right? So how can we do it, right? So we want the probability that x bar is less than 130. Well, x bar by the central limit theorem should be approximately distributed as a normal random variable because it's an average of these things. The central limit theorem applies to averages. Right? So the average should be 150, the old average. But now the standard error, standard deviation of x bar, is the individual ones divided by the square root of the sample size, which ends up 10.6, and this is also in the euros. Okay. So we can treat x bar like a normal distribution with this mean and standard deviation, and then just calculate the probability. And so one way it's usually done to do that is to standardize things, subtract the average, and divide by the standard error. The z is then a standard normal. Mean 0, variance 1 variable. That's often done because we can at least remember or think about things on the standard normal scale once we use it enough times. It's also the one that was always tabulated in books. And so this is negative 1.89. Right, it is a negative value because the average is 150. We're asking about less than 130. Maybe that's a critical cut point in terms of paying bills. Right? You want to know, or having enough money saved up to take a month off between working and going back to something else. Who knows? But under the normal curve, the normal density curve now, right? The one that has mean 0 and standard deviation 1. Here's negative 1.89. Right? And it turns out that this area that we're less than or equal to that, right, is 0.0296, or just about 3%. So if you quoted to me 3%, right, that's probably enough accuracy given this application. And so we didn't worry about what's exactly the sampling distribution. We didn't do any particular permutation. Then it kind of gets a pretty quick answer. Right? Once you know that this is almost 2, about almost negative 1.96, something like that with a few calculations after experiencing the standard normal for a few applications, you get kind of a sense that this is something that's not that unusual. What's the chance that we're greater than $170 or 170 euros?
Same.
The same. right?
It's
So,
symmetric.
yep. So we can answer other questions based on this, right? What's the probability that our average tips? Average tips is greater than 170 euros. Well, doing the same thing, that's approximately, by the central limit theorem, in here, the chance that a standard normal is greater than 170 minus our 150 over 10.6, where standard error for x bar gets used. And so it's, before it was 30, so it's a difference of 20. So this is the probability that a standard normal is greater than 1.89, and the standard normal is symmetric about, the normals are symmetric about the average, and the standard one is symmetric there. And so here's a 0, and so 1.89. The area up here is the same 0.296. So we can answer a number of different things, right? So in R, right, there's functions for dealing with the standard normal. So where's R? There it is. So right, there's a help. P norm will do the probabilities for a normal. Right? P norm here, mean 0, standard deviation. That means by default, it does the mean 0, standard deviation 1. It does the standard normal by default. Right? But you can change that. You could put 150 in there as means, and then the standard deviation of 10.6 in there. All right, and it would give you the probability. Or you can standardize itself. It, by default, does the lower tail, so less than or equal to something. Right? So you can either do 1 minus that to get the chance above it, or you can tell it lower tail equals false, and it will do it going up. Right? So let's take a look. So if I wanted the probability P norm negative 1.89 is the 0.9. Is that the number I wanted? 1.8.
It is.
0.94. I put, yeah, 296, so I don't know, maybe I copied it wrong from my thing. But anyway, if that number, let's see, 130 minus 150 divided by 10.6, negative 1.89. Okay, so maybe it should have been 0.024 instead of 0.026. So either something's going with rounding or something like that, but it's kind of giving that tail area. So the chance that under a standard normal you're less than 1.89, and so that was this picture, right? Oops. Right? That you're less than this under a standard normal. And if you put in the, if you didn't do that conversion yourself, and you put P norm 130, right, the chance that you're less than that. And you can put in 150 as the mean and 10.6 as the standard deviation, and it will give the same, almost the same value, right? So what's going on? Okay, so it's, yeah, 2.96. So maybe, maybe just that small difference in value changes the fourth decimal place, just that little bit, right? So we're reporting it to 3%. If you're really working in the National Institute of Standards and Technology and doing something with 1 billion observations and very precise measurement equipment, you might report more decimals, but at least this little example is probably enough. Right? And if you want, if you put in 170 in here, right, the other one, it's going to give you 97%, because that's less than that, right? And doing 1 minus that is going to give you the upper tail. And so you can calculate a number of things, right? If you want between two values, you can calculate the probability you're less than one of them and then subtract out the other one, right? So the chance that you're, the probability that 130 is less than x bar is less than 170. So you can do the probability that x bar is less than 170, minus the probability that x bar is less than or equal to 130. Now equals, for this normal, because of the continuity, doesn't really matter. Right? The probability you're at a particular value is effectively 0, right? Because there's no width to that. So you can take the two values, 0.97 minus 0.03, so it's about 0.94. It's about 94% of the time this individual is going to earn between 130 and 170. Assuming that the central limit theorem is accurate enough to give us this approximation. It could easily be that accurate, right? But any questions about that one? Right, we could, let me show you one other example. So in the game of roulette, I think that's the spelling. Maybe there's only one L there. Roulette, I think. Right. So the roulette is the spinner that goes around, and you put your bet on either a number or a color or some other aspect of the spinner, and there's 38 different divisions on it, and if you roll, and then a ball is rolled and spins around and eventually lands in one of those spots. And if it matches up the thing you said was going to happen, then you win, right? And so let's say you bet $10 on a number. Right? There's complicated bets of various sorts, right? But just the standard ones. You either win $10, right? Or if you lose, your money's taken away, so you're down $10. Right? There's a certain probability, but it turns out on average, the average return is negative, $0.53. Right? And the standard deviation of a single roll, you can calculate that. It's pretty big. It's 10.05 because there's such a swing between negative 10 and positive 10. And say you play 40 times. So n is 40. Well, what's the probability that you are ahead at the end of these 40 rolls, that you have a positive balance for taking all these bets? Right? What's the probability that your average is greater than or equal to 40? You might be interested in the sum. What's the total of winnings and losing? Is the total greater than, not 40, 0? Right? But if the total is greater than 40, then 0, then the average is greater than 0. Right, so this is a distribution that only has two values, right? 10 and negative 10, so it's not normal at all, right? And but we still might want to estimate this probability, right? So what do we have to do?
What do you mean?
So how would you go about calculating that one? If you wanted to use,
Approximate the sampling distribution.
Yeah, we want to approximate the sampling distribution. It's kind of like approximate the sampling distribution of a standard normal if we standardize things, right? So we're going to have this average. In the symbols, this was a mu, this was a sigma. And for n equals 40, this is the standard deviation of one spin. The standard deviation for x bar is this sigma over the square root of n for that one. So it's the 10.05 over the square root of 40, which is $1.59. So if we take the 0 minus the average, so negative 0.53 here, and then divide by the standard deviation for x bar, 1.59, right? This is kind of a side calculation. So this is going to be the probability that a standard normal is greater than or equal to 0.33. And so a standard normal greater than 0.333 is not that unusual. So in R, right, if we put just P norm, I know what I can do. Oops. You zoom in a little bit. P norm 0.33 gives us about 63%. But that would be the probability less than
So
that.
1 minus.
Yeah, if you take 1 minus, that's the probability it's bigger. All right, so about 37%. So you're going to be, it's about 0.37. 30% chance, 37% chance or so that you're above 0. If you change things, say you do 120 tries, that is 120 times, the average then for this becomes smaller, and you would put this new number in the denominator, and it turns out that the probability is less. It's about 28%, right? So as you change things, the longer you play roulette, the more sure you are to be negative. But it can be a very pleasant way to lose money if you enjoy that, right? That's the joke. Right, so that's one application of central limit theorem, right? The other place that it gets used a lot is in sample proportions. So it's not only quantitative data with averages, but if you have in trials of something, in attempts, in individuals, in cases, right? That's the sample size. Right? And each outcome, right, is binary. 1 or 0. Right? Sometimes the ones are labeled success in some way, right? And other ones are labeled failure in some way. But really it's quite arbitrary. You could be randomly picking people, and you could be counting the number of people who are unemployed. Right? So maybe 1 is unemployed, it's not really a success. Or you found somebody with a characteristic, and 1 would be that they're employed, right? Assuming they're in the labor force at all. P, a proportion, is the proportion in the population with a value of 1. Right? So the proportion who are what's the population level unemployment rate. Right? And so X is then taken as a number in the sample with a value of 1. And P hat, this X over N, is the sample proportion. And it turns out that as long as you have a large enough sample, the sampling distribution of P hat also going to be approximately normal. Right? So the central limit theorem applies to sample proportions. The sample proportion is kind of another type of average. Right? The X is the sum of zeros and ones. Right? Each person gets one value, and you add those up, zeros or ones. You divide by n. So it's like a sample average where the specific outcomes that you measure are ones or zeros. Instead of the dollar amount for each tip, it's yes or no, a binary. If n times p is greater than 10, and n times 1 minus p is greater than 10, so if the number of expected successes and expected failures are reasonably large, right? Then P hat has an approximate sampling distribution that's normal. It's centered at P, the actual population proportion. And the formula for the variance comes from the binomial probability model. It's P times 1 minus P over N. So in this case, there's a specific formula for the standard error corresponding to a binomial probability. So in some cases, the data generation, this thing with the n-independent trials, constant probability, independent, gives a binomial probability model. And so this is the formula. You've either seen binomial distribution in a class, or in introductory statistics done like a confidence interval or something for a binomial proportion, right? And it would be something like this formula. Right? So that means that anything that we want to ask a question about what's the sample proportion, what's its sampling distribution, its picture, right, is roughly normal, this distribution of p hat. It's centered at p, and then the spread depends on the, what value of p it is, and the sample size. So let's look at one numerical example right out of that. So the General Social Survey in 2012 asked people if they believed that the universe was created through a Big Bang type mechanism, some giant explosion at the beginning of time as we can see it. The General Social Survey is an ongoing large-scale survey. It's used in political science, sociology, and other fields, and it goes back, I think, about 50 years. So it has these fairly large sample sizes on all sorts of questions. Employment, health, education, other things, happiness, satisfaction, housing, but also things like, do you believe in the Big Bang, do you participate in religion? So, generally interesting, right? And so out of 372 individuals asked that, 287 said yes, the others said no. So that's a sample proportion of 0.777. Right? So we can ask a question. Right? Suppose three-quarters of the individuals in the population actually believe this. Right? They believe that the Big Bang theory is the true description or a reasonable description of the formation of the universe as we know it, right? And suppose that it really is 75%. We've been doing p-values and testing. We've asked questions like, what's the probability we're greater than or equal to our observed value if this is true? So we might have a hypothesis that p equals 0.75, and the alternative maybe that p is greater than 0.75. And more than 75% believe that, right? Well, to evaluate this, right, under the null hypothesis, p hat would be approximately distributed as a normal. If this is true, then the average value should be 0.75. And as well, the standard deviation, quite enough room. I'm just going to put a sigma here for p hat and then write it down here so there's no space. The sigma for p hat is p times 1 minus p over n, so 0.75, 1 minus 0.75 over n, which was 372 here. That thing. Do I know that number? Not exactly, right? So we'll have to calculate that, right? But then, I can calculate the probability that p hat. What's the probability that p hat is greater than or equal to 0.77? Once I know the normal distribution, right, then I can calculate the probability that we're greater than or equal to that, and that's the tail area, that's the p-value. P is getting used a lot in this, right? So we can calculate that. So, in R, So we're going to do 1 minus, let's do it in steps. So the square root of 0.75 times the 1 minus of 0.25 divided by our sample size.
372.
372, good. So 0.0224, 225, right? So a standard deviation of 0.022 plus or minus about 2%, maybe plus or minus 4% if you multiply it by the 1.96. So the p-norm, if we put, so our z-value, if we take our 0.77 we're interested in, and minus our 0.75, which is the null hypothesis value, and we put this standard error in the denominator, that gives us a z-value of 0.89. And the chance that you're less than 0.89, 8908, right, is about 81%. So the chance that you're bigger than that would be 1 minus that. So the probability that you get something at 0.77 or above is almost 19%. That's not really very unusual, right? It's almost 20%. If the null hypothesis 0.75 is really true, it wouldn't be surprising at all to get 0.77 or even a little bit bigger, right? So we couldn't really claim that 0.75 is incorrect, right? We couldn't go after a newspaper reporter that was saying something, right? That was, oh no, it's only 75%, well, whatever, you know. It's not proven that it's more than 75%. So again, that approximates the sampling distribution. The distribution of the binomial is discrete, it's at counts, it only has integer numbers, right? It's skewed, right? But it can be quite well approximated by a normal. Right? So let's put this a little bit on the notes. So this thing was 0.022 or so. This probability was the probability that a standard normal is greater than 0.89. And that ended up being about 0.18, something like that.
19.
19 was
186.
186. Good. Right. So it's not very unusual. Right, so approximating sampling distributions can help us do things. And so X bar, P hat as special cases are very useful. Right? On Monday we'll look at simulating them so we can deal with cases that don't quite, either different statistics like medians or standard deviations or something like that, or the assumptions that the central limit theorem doesn't quite hold. Right? And so it's a bit of an art, or it's not that exact in science of figuring out when the central limit theorem exactly holds. In a lot of applied settings, it will if the data are not too skewed and the sample size is reasonably large, like sample surveys of 200, 300,000 typically are okay, right? Sample sizes of 20 or 30 probably are not. And it all depends on, for the quantitative ones, what the shape looks like underneath, right? So let's just take a little picture tours here. So if I, so this binomial, right? We had n equals, so x, kind of evaluating that. The number 0 to 372. That'll be all the numbers 0 to 372. So one thing we can do is plot those numbers of x and the density, the binomial probabilities, which we're not calculating explicitly in this class, but there's a function d binom within R to do that. If we put in 372 as the sample size and 0.75 as the probability, this is what the probability distribution looks like. Right? Most of the time, it's basically 0. Right? You're not going to get, there's a 75% chance of getting ones. 75 times 400 would be 300. 75% of 372 is a little bit, a little bit less than 300. So you're not going to get 25 or 50. There's almost 0 probability of those. Almost all the probabilities in this this more range here. So if you could restrict this, say, but anyway, what this thing is, this is the sampling distribution. These are the probabilities of each of these outcomes for the number of successes. If I divided this by 372 and got a proportion, it would be in there around 75%, right? So these are the probabilities. And only certain ones are accurate, but it's fairly peaked, but it still looks pretty bell-shaped, right? And if you adjust the graph a little bit, so now let's say x goes from, what, about 275 up to 325, that's where almost all the probability is, right? And then plot that, oops, to 25 maybe. Let me go back. What should I have done? Oh, I can just line out, I can just look at this, right? So 275, maybe that's too high, 250 then. Let's do 250, and then 325 looks. So if I plot that, that's what the probability distribution looks like, right? And so it looks pretty close to bell-shaped, right? So if you imagine fitting the mean and fitting the standard deviation, you'll match it quite well, right? Now the book mentions a continuity correction, right? Because we're going from a discrete distribution that only has probability at a mass, right? At points versus a continuous curve, right? So you can make it a little bit better if you either plus or minus 0.5. Right? If you imagine kind of a blocks, like a numerical trapezoid approximation or something to this integral under this curve, right? You'd have little square blocks under those, right? And they're centered at 1, but they kind of go plus or minus 0.5. So instead of doing the probability you're less than 250 or something, right? If you do 250.5, you capture a little bit more probability. So there's a continuity correction that we can talk about in a little more detail for this approximation, but it just makes it work a little bit better when things are discrete. Right?
So is that like an error term?
It's kind of doing an adjustment because you're approximating something that's discrete. You know, if these were square bars under here, and you took it right at the middle, it would be kind of cut the bar at 280 in half. And so you can go up half or down a half to make it work out a little bit better. With this sample size, it's not going to make much difference, right? Because it's pretty fine. So you're making little tiny adjustments, right? Each of these curves going up here is not that high of a contribution to it, right? But what would happen if we only had x going up to, say, 37, right? And so our binomial, so we have 37 trials instead of 370, right? We plot x and then 337 is the maximum. That's what it looks like. So even that, is not too bad, right? Maybe it's a little bit more skew in there. We could probably restrict it to the x's to 20 and above. Right. And mostly it looks pretty good, but there's a little bit of difference at the end. In this case, this continuity correction is each one of these points has a little more probability on it because it's much more discrete. Right. So in this case, that plus or minus 0.5 on there for the interval would make that work a little bit better. So it's starting to kind of get a little fuzzy out there. So calculating in the middle is probably okay. If you're calculating in the tails, it's going to be off by a second decimal place, maybe approaching the first decimal place by one, a little bit. And if you push that further, right, in different ways. So let's say you had 0.85, right? Then it starts to look like that, right? So the kind of guidelines, right, for this one, I think this was here. Where was it? So that's roulette. So it must be here. Sample proportions. And so, okay, it's up at the top. Right. So this n times p greater than 10, n times 1 minus p greater than 10 means that you're not too far toward the edges. Right. So 0.85, 37 times 0.85 is probably less, is probably more than that, but 1 minus 0.85, 0.15 is going to be less than that. And things start to break down. So those guidelines suggest that this one, if you calculated probabilities, in the middle might still be okay, but once you get to the tails, because it's all bunched up on one side, it's not exactly normal anymore. Right? So binomials, you can study it because it's a little more restricted, right? Just N and P, and there's a fixed form of probabilities. Ordinary data, quantitative data, it's a little bit harder to study. So I was working on a bootstrap example, and then to show on Monday. Oh, okay, so I chose a nice example here. But the Veterans Administration did a survey of its, and we'll close with kind of looking at this applied example. Its employees on the topic of disaster resilience. Have they been through training? Have they been part of the Veterans Administration when there has been a disaster? Are they prepared? Are they prepared at home? Are they prepared at work? Do they know what their responsibilities are? And things like that. Right? So there's a whole bunch of questions. And this particular data set from it has just the number of seconds they spent on the survey. Right? We'll see. All right. So 554 seconds on a survey. They're doing it online, so it captures when they log in and when they log out, submit the survey. So 600 seconds would be 10 minutes. Right.
Someone spent 179 seconds?
Yeah, 3 minutes. Right. 998 was about 15 minutes or more. Right. I thought, okay, well, we'll just look at that as a distribution and we can sample from that. So, but here's the histogram of these things. Okay, seconds, I only want that column, I don't want the row numbers. So the histogram of the, seconds, it looks like that, right? Because you can't even see it, right? There's 4,026 seconds. The average looks like 910. In minutes, if you divide it by 60, that's about 15 minutes on average. There's something going on, right, for the histogram to show this. There's some incredibly large values. So these are real data. This is really what happened, and they're just getting the computer to automatically record these things, right? And so if you do a summary of that, the smallest is 93 seconds. So somebody claims to whip through the survey in 1.5 minutes, right? And maybe they answered the question, maybe they just, But anyway, they got enough of it answered.
Maximum?
The maximum was like 417,000 seconds, right? So somebody logged in, started the online survey, and a couple of days later came back and turned off the computer or something, right? Just submitted. Right? So that's real data. Sorting a random variable, right? And then taking the first 10 observations, give the smallest ones. Right? Reversing the sort, REV reverses the order. So this will get the biggest ones. Right? So the biggest ones are this one, 154,000, some others. If you divide it by 60 and then by 60 again, right, it turns it into minutes and then hours. Right? So some people, were 6 hours, 7 hours, 24 hours. So some people, it was just on hold, for a couple days. And for this one, somebody had it, started it and didn't submit it or finish it. Somehow it was still active on their computer. And that's just, they might have submitted a legitimate survey with legitimate answers and valid data, but that just recording of seconds is kind of completely out the window. Right? So sometimes you get crazy data like this. And so if you wanted to simulate, so say instead of getting all 4,000, right, imagine you did a pilot study on 40 people. Right? You get 40 employees to take it. You want to see how long is this going to take you. Right? As you estimate burden, how much time will the employees doing this. Right? If the survey is going to take 2 hours, right, for every person, that's a lot of employee time spent doing this thing. Is it worth it? So let's say it's tested on 40 people. Right. And here, I was going to do this on Monday. We might still come back and look at this for Bootstrap as kind of a difficult case after we look at a more rational case. And I take a sample of size 40. Here's the 40 sample values. It did get one value that's pretty large. Here's a histogram of what the value is. So it kind of looks funny because of that one there. But it gives an average of, well, did I not run that one? No, it's a little different than I had before. But about 1,000 seconds in terms of minutes, about 17 minutes as an average. It's not too different from the actual 15, but that average, the population average of 15 includes those ones where they just didn't turn off their computer, right? Well, what's the sampling distribution of X bar? Right? So let's generate, since we have that 4,000 data, we can take different random samples, right? We can actually get the sampling distribution. We can at least simulate it, right? Even if we can't, even if we don't want to do it. So let's generate 1,000 samples. Let's get 1,000 means. We're going to go through that loop, and each time we're going to take a sample without replacement, or without replacement, because just like you would in a sample survey, of 40 people. And let's look at the histogram of those means. And so the sampling distribution of sample size 40 is extremely skewed. Right? If you happen to get one of those enormous values in there, it overcomes the other 40, right? The other 39, and produce. And if you get two of the very big values, get probably one very big value, two very big values, three or more very big values in your sample, just by chance, it throws everything off, and it's not normal at all. Right? So sample size 4, I think this would probably persist a sample size of 80 or 120, just because there's those ludicrously large values in there. Right? If you actually wanted to analyze this, you have to make a decision. Do you want to cap it at 24 hours? Cap it at 7 hours? There's kind of a break in the data. So if I do this reverse sort, where was that?
Down.
That was down. Put that there. That was
Nope.
mean, that was at the bottom, right? This reverse sort thing, I'll do it in hours, it's easier to see. It's kind of there's some that were kind of 24 hours and something like that, but then, if you cut it at, below 7 hours, that eliminates, it looks like 10 out of the 4,000 values, where it appears for anything rational that computer got left on, or they just didn't submit it. And it doesn't really take that long to do it. It's I don't know of a good way to say, subject matter. You got to understand the subject matter. Is it rational to ever have a value more than, a couple hours on this? I mean, some people will take a while to do a survey and do it a lot longer than you would expect. If you aim it for 15 minutes, they could be on it for a couple hours, thinking about every question, reading every detail. And so for them, that is true. Right? Not for most people, but for some people. 17 hours though, 18 hours, there gets to be these outliers that, you kind of worry about the other side. If somebody came in at 15 seconds, you'd say, wait, somehow you got complete data or got enough data to be analyzed, but got to the last screen and submitted it. But there's something funny about that too. Either there's a recording process, because the IP address is, who knows how good the computer recording is. Anyway, so actually analyzing it, I don't think anybody would object to dropping the target, the largest one. Maybe not the next one that's more than a day. Maybe, at some point you have to say, okay, the data have to be included because it represents what somebody actually would do or we'd expect, and not just an error, kind of the recording thing. They got called away to do something and left it there and then came back. Right? But anyway, even with this distribution, if you took samples of size 1,000, central limit theorem very well could still apply, and the distribution would be quite normal. But it's way beyond the standard 40 or 60 cases, and it depends on the data. So approximations work very well and are used all the time for things, but being aware of how extreme your data is makes a big difference. So we'll come back on Monday and look at this bootstrap, probably with a more rational example, and then see what happened in this one. Thank you very much.
See you at,
It's 2 weeks from now, but I wanted to make you aware of it.
Okay.
My brother's wedding is
Okay.
back in Massachusetts,
All right.
so I have to leave. It's the 20th. I have to leave that Friday, like before
Okay.
class, to get down.
That'd be fine.
So,
So
okay.
be great. So-
And then I think I should be back on Monday in time for class.
Okay.
Because the wedding is like Sunday, but I have to go down early because
Yeah. You're in the ceremony.
yeah,
So.
all that. So
The older brother.
yeah,
Yeah.
he's 29 now. So thank
Good.
you.
Well, that's exciting. So,
Yeah.
yeah. So Tegrity is supposed to record it and post notes and any handouts and things before. So,
Okay.
if you need. So yeah, that Monday, Tuesday, after that time, if you have questions,
Yeah.
you can try to arrange some other office hours if it
Okay.
works.
Thank you.
Yep. Yes.
I have a similar comment. I just wanted to let you know I won't be in class on Monday. 'Cause
Okay.
I have to go home this weekend.
Okay.
So I'm gonna miss like both classes.
Okay.
But I'm actually leaving like right after the presentation later
Oh,
today.
all right.
But,
All right.
yeah. So I just want to let you know.
Okay. Hopefully things are all right, or.
Oh yeah, things
Yeah.
are good. I just have to be home, but
Yeah, sure.
it's okay.
Yeah.
But I'll take a look at the videos and all that
Okay.
good stuff.
Yeah,
So
I'll be posted. So.
yes. Okay. See
Yep.
you in 15.
Yeah. See you soon.